Good morning, everybody. It's my pleasure today to present you some of our work at NTP on urban construction. So how to build with earth? So first we need to have earth covering, if possible near the construction site, and earth is a soil or subsoil that is used raw in order to construct building, and whose cohesion is mainly ensured by the presence of clays. After this gathering, we can condition the earth if it's necessary and build the walls using several techniques like cob, adobe, rammed earth, and plenty others. But all these construction techniques have in common to be green because the embodied energy is very low and the earth which is used can be directly reused for new construction. In addition, if we look at the building heritage, we can see that we can build very durable urban construction. For example, the Great Wall of China, among others. And if we look at these two pictures, we can see that we can use earth as well to make very modern architecture, which is very impressive and interesting. However, when we think about urban construction, most of the time we have this picture in mind, which is picture of collapse. And this collapse are most of the time due to an abnormal amount of water content within the material. That's why my main topic, the main topic of this talk, will be the role played by water in all its form and the behavior of the material. And this water can be benefits for the material behavior. It is the case of hygroscopic behavior, or can be a drawback. This is the case of the impact of water on mechanical behavior. And in the third point of this presentation, we will talk about some way to reduce the negative impact of water on urban constructions. So first, earth is an hygroscopic material. One definition can be that this material can passively regulate the indoor relative humidity, which is very important in order to improve the indoor air quality. For that purpose, the material should be permeable in order to allow exchange between the indoor atmosphere and the material. And thanks to its network of macropores, urban materials are very permeable. For example, the permeability to vapor of urban material are 10 to 100 times higher than those of concrete. However, permeability is not sufficient. The material must have as well good suction properties. The suction property is the amount of water that the material can take in function of the relative humidity in which the material is. And the relative humidity is the amount of vapor in the air divided by the maximum amount of vapor that the air can contain. So we can see in this graph, for example, that compacted earth blocks can have about 80 kilograms of water per cubic meter of material if it is submitted to an atmosphere at 90% of relative humidity. One other thing that we can see in this graph is that for each material there is two curves. There is one curve which is the increase of water mass within the material in function when the relative humidity increases, and the second curve which is the decrease of mass of the material when the relative humidity decreases. The first one is called the adsorption curve and the second one the desorption curves. And there is a difference between both. First, a question arises, which is which curve we need to use in order to correctly model the material, the adsorption curve, desorption curve, or something between them. To analyze that point, we have made a test when we have put a sample in a climatic chamber and we have made some cycle of relative humidity between 33% and 75%. During this cycle, we have measured the mass of the material and we have measured the relative humidity within the sample at 2 cm and 4 cm depth in order to see the progression of water vapor through the material. And this is the result obtained. This is the variation of relative humidity at 2 cm depth, the variation of relative humidity at 4 cm depth, and this is the mass variation of the sample. And we have tried to model this test using the water mass conservation equation and the FM code comes. And as an input parameter, we first choose the adsorption curve directly of the material. And we can see that numerical results are far from experimental results. First, we have made a second calculation where we use cycle of relative humidity between 23 and 85% of relative humidity. And in such case, we can see that the experimental results are very close to numerical calculations. The conclusion of that is that the adsorption isotherm, which is actually one of the most important parameters for hydrothermal modeling, should not be taken in a fixed way, but it should correspond to the real condition in which the material will be solicited. And it's very important to do that, if we want to make some accurate simulation. Let's now talk about the second part of this presentation, which is the impact of water content on the mechanical behavior. To illustrate that point, we can use this graph, which depicted the variation of unconfined compressing strength of rammed sample in function of its water content. And the water content here is expressed as the mass of water per unit of dry mass of the material. What we can see is that when the water content is too important, the strength almost vanished. But what is important as well is to study what happened in this range of water content there, which corresponds to a variation of water content due to the variation of air humidity. To test that, we have made some triaxial experiment at controlled relative humidity and temperature on a compacted earth sample. And what we can see is that when the relative humidity of the air increases, the stress-strain relation changes a lot. At first, the strength of the material is changed. You can see quite important variation of strength when relative humidity increases. But what we can see as well is that there is a variation of stiffness of the material because when relative humidity increases, the Young modulus decreases. Another point is that we made some cycle of loading and unloading at several stress levels. And what we can see is that with increasing loadings, the Young modulus measured with this loading and unloading cycles decrease, which is not some kind of damage. But this damage is all the more important when the material is dry, okay? So, which is when it is equilibrated at a low relative humidity. When it is equilibrated at a high relative humidity, which is the blue curve here, there is almost no more damage. So, it denotes that the earthen material have a quite complex hygromechanical behavior, which exhibit both damage and plasticity, because we can see here some residual strain when we make some loading and unloading cycles. And all the way to model this system is not yet totally understood by the scientific community, and so more studies are needed on that point. Now, does this impact of water content become even more important at sub-zero temperature? To test that point, we have made the first analysis of samples which are frozen during 1 day at minus 23 degrees, and then thawed either in a moist room at 100% of relative humidity or in contact with liquid water. These samples were compared to reference samples, which are basically tested the same, but which were sealed and stored at 23 degrees during 1 day instead of being frozen. The results here lead that for the reference sample, we can see an increase of water content due to their storage in a moist room or their contact with liquid water, but no damage occur on this reference sample. On the other side, for the sample submitted to freezing drying cycle, we can see that the increase of water content is much more important, and that damage and crush down of the sample occurs only after 2 cycles of relative humidity. This phenomena can be explained by the cryosession effect. Actually, the pressure of the water that remains liquid within the sample will be very low and even under zero because of the equilibrium with the ice crystal, which is at the vicinity of the surface. And since the water within the water tank, for example, is at the atmospheric pressure, there will be a gradient of pressure that will generate some suction of water within the material, and so the increase of its water content. One second point we wanted to test is the behavior of material due to freezing drying cycle, but at constant water content. For that purpose, we have put in climatic chambers several samples, and we have measured their strain during cycle of temperature between minus 20 degree and plus 10 degree. And the sample were equilibrated at several water content, either dried, the black, equilibrated at 2 relative humidity, which have the gray and the orange curves, or saturated at several saturation, but quite high saturation, so 75%, 85%, and 96%. What we can see is that for the dry sample or the sample equilibrated at a given relative humidity, there is almost no impact of freezing drawing behavior on the strain, because it's purely thermal contraction that we observed. But on the other samples, the one equilibrated at higher saturation, we can see a quite high contraction during the freezing drawing cycle. So this contraction can be explained in the same way as the cryosuction effect, but at the pore scale, where we can see that the liquid, but the water that remains liquid within the pore system will be under pressure, and so it will generate some contraction of the material. And what it is as well important to underline is that at the end of the cycle there is some residual strain. So this residual strain may stabilize or may increase with an increasing number of freezing drawing cycle, which may induce a problem of stability of the overall structure. So these 2 points show that, okay, there can be some problem of freezing drawing durability of oven construction, but the way to assess the problem will be far different from the way we use to estimate the freezing drawing durability of saturated concrete. To conclude on that part, we can say that, okay, we have seen that the water impact a lot the material, in particular its mechanical property and its durability. We have seen here the durability to freezing drawing cycles, but there is as well other durability problem due to water, like erosion and so on and so forth. So the best way to prevent this disease will be to prevent the wetting of the material, and to do that, to use an appropriate architecture. It is really what is the best option when it's possible. But sometimes it's not possible. So there is 2 other approaches that can be done. One will be to put some additive on the material in order to increase its resistance to water. And the second one will be to protect, with plasters, for example, the material from water. So the modification of the material to increase its resistance to water has been studied since decades, and most of the time it is cement or lime that are used, and so we add about 5 to 10% of cement of lime to earth, and it increases its resistance, and it increases its resistance to water as well. But the problem is that to put some hydraulic binder in the earth reduce its ecological assets, reduce its reusability, and it is not always efficient. We have tested here, for example, with a cyclic drip test, which is a test to estimate the durability to erosion, and we can see that with the same cement and the same dosage, but for 2 different earths, that for one earth, okay, the resistance to erosion is perfect, while for another one, we can see that there is some erosion problem. So we need to have some research in order to improve this stabilization of earth in order to make it always efficient. And this kind of observation can be made as well for biostabilization system, which is a new kind of stabilization using, for example, biopolymers to reduce the sensitivity to water. In such case, there is also a problem of optimization of the formulation. But I want here to underline a possible way to reduce the sensibility to water. It's surface texturation. For that, we have tested 2 materials, and we have analyzed the water droplet penetration at the surface of sample in function of their rugosity. And we can see that for the sample with the lowest rugosity, there is an oscillating behavior of the droplet at the surface, while for the other there is much more occasioned behavior. To go further on that point, we have made a collaboration with Institut Navier and University Gustave Eiffel to analyze the droplet penetration within the sample with X-ray microtomograph. And we can see that the lower the rugosity is, the lower the penetration of the droplet at the surface will be. After that initial stage, the progressive penetration of the droplet will be clearly a consequence of the permeability of the material, which is here depicted by the AA value. So these results show that there is a way to reduce the sensibility of water of Earth by modifying its surface texturation and without any addition to the Earth. Okay, I will conclude my presentation by saying that since the last decade, there will be important advances on urban construction. One way to see all of these advances is to look at the state-of-the-art report we have written within the framework of the Rilem Technical Committee of urban material. But it still lacks some consensus on the method that should be used to assess the performance. And one other point I want to underline is that is the last part of my presentation, that will be new urban material, and we need to go through optimization of this new material, and it's quite important that all of these points, so the development of a new method to test the performance of the material, as well as the definition of new urban material, will be studied in the framework of Rilem. Okay, thank you for your attention.